Welcome back to the Professor Insight podcast, the space where we explore the intersection of artificial intelligence, neuroscience, and emerging technology, and turn it into something practical for your business, your strategy, and your everyday thinking. I'm your host, Professor Billy. As always, a quick note before we begin. This podcast is fully powered by AI tools, from content creation to script writing and voice generation. And yes, what you're hearing right now is a voice clone of me, brought to life with full human oversight and manual curation. Before we dive in, let's get clear on a term you've probably been hearing a lot lately: synthetic data. At its simplest, synthetic data is information generated by algorithms rather than collected from real people or real-world events. Instead of surveying 1,000 consumers or running a costly clinical trial, you can ask an AI system to produce simulated responses that look like they came from actual participants. Think of it as an artificial mirror of human behavior, constructed from patterns the model has already learned. Now, here's why it's generating so much excitement. Synthetic data promises speed, scale, and efficiency. Businesses can run virtual focus groups overnight. Researchers can collect millions of data points without worrying about recruitment, privacy, or fatigue. For policymakers, synthetic data seems like a way to sidestep ethical and logistical barriers. In other words, it's being pitched as the shortcut to insights. Cheaper, faster, cleaner than dealing with real humans. But that's where the debate begins. Today's episode digs into an unpublished paper titled "Large Language Models Do Not Simulate Human Psychology" by Sarah Schroeder, Thekla Morgenroth, Ulrike Kuhl, Valerie Vaquet, and Benjamin Parson. Since 2018, and especially since the explosion of ChatGPT in 2022, large language models have been woven into almost every field: education, marketing, even science itself. Some academics have even gone so far as to list ChatGPT as a co-author on published work, and more recently, researchers have started treating LLMs as participants in psychological studies, as if they could replace human subjects altogether. But here's the punchline of this paper: they can't. Now, to be clear, this paper isn't written for marketers or business leaders. It comes directly out of the world of psychology research, where scholars are wrestling with whether large language models can stand in for human participants in experiments. The context here is academic: moral judgment tasks, subtle shifts in wording, and the reliability of simulated responses in controlled studies. But don't let that fool you. The implications spill far beyond psychology. If these models can't reliably capture human nuance in a lab setting, what does that mean for businesses that are tempted to swap out messy, costly consumer research with neat synthetic data? What happens when brands start testing ad concepts or product ideas on machines that don't actually think or feel like people? Why this matters right now is simple. If we in marketing, consumer neuroscience, or academic research start trusting synthetic data too much, we risk mistaking statistical patterns for genuine human thought. The authors show that while models may mimic human answers in familiar scenarios, they crumble when meaning shifts subtly. They miss cultural nuance, smooth over diversity, and treat language tokens as interchangeable, something no human mind would do. In this episode, we'll unpack 3 big insights. First, why LLMs look human-like in some tasks, but fail when tested on subtle variations. Second, the deeper machine learning limits that explain why true psychological simulation is out of reach. And third, what this means for us, how synthetic data can support research and marketing workflows, but why it should never be mistaken for the real thing. Let's dive in.
Welcome back to the Deep Dive. If you've spent any time online recently, you know large language models, or LLMs like ChatGPT, are truly pervasive.
They really are everywhere.
Helping write code, summarize documents, brainstorm ideas. Capabilities that just a few years ago felt like pure science fiction.
Absolutely.
And this incredible performance has even led to research suggesting these AI models could potentially replace human participants in studies. It sounds remarkably efficient, doesn't it?
On the surface, yes. Very appealing.
Okay, let's unpack this. Today we're taking a deep dive into a fascinating, highly rigorous journal article. It's titled "Large Language Models Do Not Simulate Human Psychology." And this paper raises some very pointed questions about this initial exciting claims regarding AI's ability to truly stand in for us.
Indeed. While the impressive capabilities of LLMs are, undeniable, This deep dive's mission is to critically examine the core question posed by this research. Can these models truly replicate the intricate nuances of human thought and behavior?
Or are we perhaps overestimating their abilities when it comes to the complexities of the human mind?
Exactly. Are we maybe getting a bit ahead of ourselves?
Yeah.
We're here to help you discern the hype from the foundational reality.
And to do that, we've meticulously extracted the most important insights from this academic paper, which presents both strong conceptual arguments and some pretty surprising empirical evidence.
Right.
Our goal is for you to walk away from this deep dive thoroughly well-informed on this captivating and, for some, perhaps a little unsettling topic.
It should be interesting.
It's quite easy to understand why the idea of LLMs simulating human psychology gains so much momentum, though. Just imagine the allure for researchers.
Oh, definitely.
You could potentially save enormous amounts of time and money.
Huge amounts.
And bypass many of the tricky privacy issues that come with collecting human participant data.
Right. The IRB hurdles, the consent forms, all of that.
The thought of running a large-scale study with what seems like an infinitely available AI sample was, understandably, incredibly attractive.
Absolutely. And early research really seemed to, validate that optimism. Consider the work by Dillian and colleagues. They investigated moral judgments and discovered that GPT-3.5's ratings showed a striking correlation of 0.95 with human moral judgments across hundreds of different scenarios.
Wow, 0.95, that's almost perfect alignment.
It's incredibly high. Think about that.
Yeah.
Almost a perfect match. What was particularly compelling was how consistently this strong correlation appeared across various demographic groups.
So it wasn't just one specific group it matched well.
No, it seemed pretty robust across different demographics. On the surface, it truly suggested that AI models could be excellent stand-ins for human study participants, at least in, structured scenario-driven tasks.
That's a staggering correlation. If AI is perceived as that close to human moral judgment, why aren't we just handing over all our ethical dilemmas to them?
Well, yeah.
What did subsequent research or developments reveal that kept this promising picture going? Because it didn't just stop there, did it?
Good question. No, it didn't stop there. Later developments continued to build on this. Dillian and all. In more recent work, even found that human participants perceived GPT-4's moral reasoning as slightly superior.
Superior? Really?
Yes. Superior in terms of morality, trustworthiness, and correctness compared to a representative American sample and even an expert ethicist.
Wow. So people thought the AI was better at moral reasoning.
In some ways, yes, according to that study. Now, people could still distinguish AI-generated responses from human ones, so it wasn't a perfect imitation.
Okay, so not indistinguishable.
Not indistinguishable, but the perceived quality was remarkable. And it wasn't just general-purpose models either. There was the development of specialized models, like CENTAUR, for example.
CENTAUR, tell me about that.
This model was initialized with the powerful Llama 3.1 70B LLM.
A big model.
A very big, capable model. And then it was fine-tuned on approximately 10 million human responses from 160 different experiments.
10 million responses. That's a huge amount of human data to learn from.
It really is. And the claims around CENTAUR were bold. That it could predict and simulate human behavior in any experiment expressible in natural language.
Any experiment. That's ambitious.
Extremely ambitious. So all of this indeed painted a very promising landscape for, synthetic data solutions. The idea that AI could generate data that looks just like human data.
With all that initial promise, it's easy to get swept up in the idea that LLMs are almost miniature digital humans, ready to replicate our every thought and judgment.
It really is easy to see why people thought that.
But what did this paper uncover that fundamentally challenges that perception? Here's where it gets really interesting. Where does this apparent human-like behavior start to break down?
Right, that's the crucial question. And it really comes down to the fundamental nature of an LLM. At its heart, an LLM's job is surprisingly simple, conceptually at least.
Okay.
It predicts the most probable next word, or more precisely, the next token, which is, a unit of text, could be a whole word, part of a word, even punctuation.
Right, the building blocks of the text.
Exactly. It predicts the next token in a given sequence. And crucially, it does this based purely on statistical probabilities learned from its vast training data.
Billions, trillions of examples.
Without any true conceptual understanding of meaning or truth.
So they're essentially incredibly sophisticated pattern matchers, not true thinkers. Is that fair?
That's a very good way to put it, precisely. Think of it like this. For any input text, The LLM determines the statistical likelihood of billions of possible words or tokens that could follow. Then it essentially, rolls a die with billions of sides, metaphorically speaking, to pick the next one based on those probabilities.
Okay.
This powerful probabilistic approach allows LLMs to generate text that looks coherent and plausible, often remarkably so. But it's not because they understand in a human sense.
Got it.
And this next token prediction reality leads to several significant shortcomings when we try to use them to simulate human psychology.
Can you give us some examples of where this core mechanism falls short? Where does the simulation start to look less human?
Certainly. For instance, LLMs don't always react to instructions in the way a human would intend. They don't quite get the spirit of the instruction sometimes. One study on recommender systems, for example, found that for LLMs to accurately simulate users, the prompts needed to be extensive and highly detailed, really spelling things out.
So you couldn't just give it a simple instruction.
Simpler prompts often led to inaccurate recommendations. It also showed that LLM moral judgments, going back to that, can shift much more dramatically based on subtle framing effects in a scenario than human judgments do.
So changing a few words could throw the LLM off more than a person.
Exactly. Humans are far more robust to these framing changes than LLMs, which indicates a difference in how they interpret the underlying meaning versus just the surface text.
That's fascinating. And what about consistency across different interactions? If they're just predicting the next token, wouldn't they be incredibly consistent in their responses? This paper suggests otherwise.
You'd think so, wouldn't you? But this lack of consistency, or maybe a different kind of consistency, is another significant red flag. The research shows that LLMs can be inconsistent across simulations.
How so?
Well, if you rephrase a prompt slightly, even keeping the meaning the same, or if you switch to a different LLM model, you might get vastly different results.
Right.
In experiments like the dictator game, which explores human fairness and altruism.
Yeah, where you decide how to split money.
Precisely. Assigning human-like identities or personas to LLMs didn't lead to consistent human-like behavior. Their actions were highly sensitive to how the prompt was formulated, highlighting their reliance on superficial textual cues rather than a deeper understanding of fairness or social roles.
Okay, so very sensitive to the exact wording.
Very sensitive. Furthermore, LLMs genuinely struggle to capture the full variance and diversity of human responses. Even when prompted with different personas, they often fall short.
They don't capture the full spectrum of opinions?
Kind of. For example, when comparing interviews with human podcast creators to those with ChatGPT-generated personas, the AI-generated responses, while they sounded credible,
plausible, yeah,
they lacked the clear-cut opinions that were evident in the human data. They tended to be more generic, maybe a bit bland, reducing the natural diversity of strong opinions you'd find in real humans.
Interesting.
And another study showed that LLMs failed to simulate cultural diversity effectively, even when they were given specific persona prompts trying to elicit that.
So they tend to smooth out the edges, losing that rich tapestry of human individuality and nuance.
That's a good way to describe it. They regress towards a mean, in a way.
And what about those moments when LLMs just make things up? We often call them hallucinations. How does that fit into this picture of not simulating humans well?
Right. Hallucinations, factually incorrect or fictional content that appears convincing, aren't errors in the traditional sense for an LLM. It's not like a calculation mistake. They're an inherent part of the text generation process. An LLM simply generates text based on probabilities to create plausible sequences. It doesn't have an internal mechanism to distinguish between what's factual and what's fictional.
So it just generates what's statistically likely, which might happen to be true or might not.
Exactly. The output just happens to be factual in many cases because it matches patterns in its training data. This means, without a separate validation mechanism, you can't truly tell what's true from the LLM's perspective. This makes them unreliable for studies requiring factual accuracy or consistent truthfulness.
That makes sense.
But the paper introduces a truly crucial theoretical argument from a machine learning perspective. The generalization problem. This is really core to their argument.
The generalization problem. Okay, break that down for us.
Sure. In machine learning, generalization means performing well on unseen data. Data the model wasn't explicitly trained on.
Right, how well it adapts.
For LLMs, generalization is expected for similar token sequences, that is, text that looks statistically like what it was trained on. If you give it a sentence very similar in structure and wording to sentences it saw millions of times, it'll likely handle it well.
Okay.
However, there's no guarantee that this generalization holds in the space of meaning or for novel tasks.
Meaning if the underlying concept is different, even if the words are similar.
Precisely. Think of it this way. Teaching a child to tie their shoes means they can tie any pair of shoes, right? Even ones they've never seen before. That's human generalization understanding the concept of shoe tying.
Got it.
For LLMs, their shoe tying ability only really applies reliably to shoes, meaning text prompts that look almost identical, statistically speaking, to the ones they trained on. Using LLMs to simulate human psychology often requires them to extrapolate far beyond their training data, behaving like humans in entirely new experimental setups or slightly altered scenarios.
And that's the leap they struggle with.
This is precisely what these models aren't reliably designed to do. They're designed for interpolation within the data distribution they learned, not necessarily extrapolation to new conceptual spaces.
That's a critical distinction. Can you give us a concrete example of this generalization failure in action?
Absolutely. You can see this failure in action with subtle differences. Older language models, for instance, often struggled with negations like good versus bad.
How so?
They might treat them as very similar tokens because they often appear in similar contexts in the training data, even though they're opposites in meaning. So the statistical similarity overrides the semantic opposition.
Right.
While larger, newer models have certainly improved on this specific issue, these kinds of failures still occur with prompts that genuinely go beyond their training data in subtle ways.
Okay. Any other examples?
Another illuminating example comes from theory of mind tests, which assess the ability to understand others' mental states, like knowing someone else doesn't know something you know.
Right, the classic Sally Ann test kind of thing.
Exactly. Early research claimed LLMs might possess theory of mind because they responded similarly to, say, 9-year-old children in some standard tests.
Which sounds impressive.
It does. However, further studies show that subtle variations in the test vignettes, things that change the core logic, but maybe not the surface words, drastically like describing transparent containers where someone could see inside.
Changing a key condition.
Yes. These subtle but crucial variations were often ignored by LLMs, leading to absurd responses that didn't make logical sense if you understood the situation. This strongly suggests that LLMs are relying on simple token similarity, matching patterns from the original tests they likely saw in training, rather than a human-like understanding of meaning or mental states.
So they learned the pattern of the test, not the principle behind it.
That seems to be the case.
These theoretical arguments are compelling, but the paper doesn't start there, does it? It provides concrete empirical evidence that really drives home the point. They conducted a defining experiment, and the results are quite striking.
Indeed, they did. This is where the rubber meets the road, so to speak. They started by replicating Dillian and colleagues' original findings, the ones with the high moral judgment correlations.
Okay, establish the baseline.
Exactly. And they confirmed it. They found that LLMs did show a very high correlation with human moral judgments for the original scenarios, which were likely, quite similar to the kinds of text the LLMs saw in their vast training data. So this initial part worked as expected.
Okay, so far so good for the LLMs. But then came the critical test, right? What did they do differently?
Exactly. Here's where the ingenious twist came in. They then introduced slight rewordings to these moral scenarios. Sometimes it was as little as changing a single letter.
Just one letter?
Sometimes, yes. But these changes were very carefully designed to alter the semantic meaning significantly while keeping the token sequences, the actual string of words, very, very similar to the originals.
So testing that generalization problem directly, similar text, different meaning.
Precisely. Testing whether the models react to the meaning or just the surface form.
And the contrast. How did humans and LLMs respond to these subtle but meaningful changes? This must be the key finding.
The contrast was truly striking. Humans, as you'd expect, accounted for the shift in meaning and changed their moral ratings accordingly. The correlation between their ratings for the original and the reworded items dropped significantly, down to around 0.54.
Okay, so a much lower correlation showing humans reacted to the meaning change.
Exactly. It clearly shows humans reacted strongly to the nuanced meaning and the ethical implications of the rewording.
And the LLMs? How did GPT-3.5 and GPT-4 handle it?
LLMs, on the other hand, specifically GPT-3.5 Turbo and GPT-4 Mini, the very models that showed such high initial correlations were hardly affected by these rewordings. It was quite remarkable.
Hardly affected, so their rating stayed similar even when the meaning changed drastically?
Pretty much. Their correlation between the original and the reworded items remained surprisingly high. For GPT 3.5, it was still around 0.89.
0.89, compared to 0.54 for humans.
Yes. And for GPT-4, it was an astonishing 0.99, almost perfect correlation, meaning it basically treated the original and the meaningfully altered scenario as identical.
Wow. That powerfully reflects their reliance on textual similarity, not semantic understanding.
Absolutely. And when they measured the amount of change, the mean absolute shift in ratings, humans showed a large mean shift of 2.20 points on the rating scale. They reacted strongly.
Okay.
LLMs, by contrast, had much smaller shifts. GPT-4 only shifted by 0.42 points on average. Even CENTAUR, the fine-tuned model, only shifted by 1.25 points better than GPT-4, but still much less than humans.
Those numbers are truly telling. It's not just about correlation, but the magnitude of the reaction. Let's make this even more concrete with a couple of examples directly from the study. How did humans and LLMs differ on specific scenarios?
Okay, absolutely. One example involved prisoners. Humans saw freeing wrongfully convicted prisoners as a moral act, which makes perfect sense, right?
Of course.
But they viewed freeing rightfully convicted prisoners as unethical, a clear distinction.
A crucial one.
LLMs, however, viewed them as largely equally moral. They completely overlooked that crucial distinction wrongfully versus rightfully because the surrounding words were so similar.
That's a huge ethical difference that the LLMs just didn't pick up on based on potentially just one word change. What was another illuminating example?
Another one involved animals. Humans considered setting traps to catch stray cats unethical.
Generally, yes.
But setting traps to catch rats, they viewed as ethical, or at least much more acceptable. Again, a clear, logical human distinction based on context, species, potential harm, etc.
Right. Practical pest control versus harming pets.
But LLMs, they viewed both setting traps to catch cats and setting traps to catch rats as similarly unethical.
So, again, missing the nuance completely.
Exactly. It demonstrates that LLMs consistently overlooked crucial ethical and practical distinctions that humans readily make, simply because the underlying token sequences remained very similar, even if the meaning completely changed. So what does this all mean? It shows this deep reliance on the text itself, not the underlying concept.
And what about CENTAUR, the specialized model you mentioned earlier, the one fine-tuned on millions of human responses? Surely it did better.
That's what you might expect, and it's particularly telling. Even CENTAUR, the model specifically designed and fine-tuned to simulate human psychological responses, performed very similarly to its base model, Llama 3.170B.
The one it was built on.
Yes. And it showed the same limitations in these reworded scenarios. It was better than the base GPT models in terms of shift magnitude, as I mentioned, but still far off from human sensitivity and still showed very high correlations between original and reworded items.
So even throwing 10 million human responses at it didn't solve this fundamental problem.
It highlights that mere fine-tuning, even on massive data sets of human behavior, might not bridge this fundamental gap in semantic understanding. It suggests synthetic data solutions built on LLMs may not be as robust as we might hope for modeling complex, nuanced human behavior, especially when situations deviate even slightly from the training data patterns.
Right. Okay, this is incredibly insightful. So if you're using AI in your daily life, maybe in your work, or perhaps you're thinking about using it for some kind of research, what does all this mean for you? How can we apply these insights to use AI more effectively and avoid some of these surprising pitfalls?
Yeah, that's the key question for listeners. The most important takeaway, the headline really is this: do not treat LLMs as reliable human simulators.
Just fundamentally don't make that assumption.
Don't make that assumption. They are not reliable replacements for human participants, especially in psychological studies or any task requiring genuine human understanding or judgment. While their text generation can be incredibly convincing and appear human-like, their underlying mechanism is fundamentally different from human cognition.
So we shouldn't dismiss them entirely. They're clearly useful tools, but approach them with a certain perspective, a healthy dose of skepticism.
Exactly. Frame LLMs as valuable tools. Yes, because they are. But view them as fundamentally unreliable ones when it comes to replicating human-like cognition, particularly in novel or nuanced situations, or situations where the meaning is paramount over the form.
Okay.
They can assist with many tasks: brainstorming, drafting, summarizing, even coding. But they cannot replace the core human element of understanding, judgment, and sensitivity to meaning.
Which leads to?
This leads to the absolute necessity to validate. You simply must validate all LLM outputs if accuracy, truth, or genuine human-like response matters.
Don't just trust the output blindly.
Never trust it blindly for critical applications.
Yeah.
LLMs can absolutely assist with tasks like brainstorming ideas, maybe pilot testing questionnaires to see if the wording is confusing, refining experimental materials, or even automating well-validated data annotation steps where the criteria are extremely clear and objective.
Okay, so assisting, not replacing the judgment.
Precisely. But, and this is crucial, their outputs must always be cross-checked with human data or human understanding. You, the human user, need to be the ultimate arbiter of truth, relevance, and accuracy.
That makes perfect sense. What are some practical best practices that emerge directly from this research for anyone interacting with AI, whether it's just using ChatGPT or something more involved?
Okay, based on this and related research, several best practices become clear for users of AI. First, deliberately vary your prompts. Don't just use one phrasing. Try rephrasing your request to check for consistency in the LLM's responses. If slight changes give wildly different answers, that's a red flag.
Test its robustness.
Exactly. Second, always keep precise records. Note down the exact prompt text you use, the specific model version, because models change over time.
Like GPT 3.5 versus GPT-4 versus GPT-4.
Right, and record all the parameter settings you use, like temperature or top out if applicable. This is crucial for reproducibility and for understanding later why you got a certain result. Good scientific practice, basically. Essentially, yes. Third, don't just stick to one LLM. If possible, evaluate different models for a given task. One might be better suited or reveal different weaknesses than another.
Compare their outputs.
Compare them. And finally, the big one. Always validate LLM outputs against manually produced data or expert human judgment, even if it's just on a small sample or spot checking. This goes for anyone using AI for critical tasks, whether in research, business, writing, or even just gathering important information.
So maintain vigilance.
Maintain vigilance and encourage what we might call a healthy distrust of LLMs, especially when the stakes are high. Users need sufficient skill and domain knowledge in their area to be able to manually validate LLM behavior and output. You need to understand their limitations, not just be amazed by their strengths.
You need to be smarter than the tool, in a sense.
In a very important sense, yes. You need the expertise to judge the output. And this brings up an ethical point. Humans remain the responsible authors of research, reports, decisions. You should fully understand and be able to validate any AI-assisted work you produce. You can't just blame the AI if it's wrong.
The buck stops with the human user.
Absolutely.
Okay, let's try to summarize then. While large language models are undeniably impressive, really excelling at processing and generating text that looks incredibly human-like,
often indistinguishably so on the surface,
their underlying mechanism, predicting the next token based on probability, means they don't truly understand meaning or human psychology in the way we do. They're not getting it.
Exactly. And this fundamental difference means they generalize based on textual similarity, the patterns of words, not semantic understanding, the actual meaning behind those words.
Right.
And that core distinction leads to significant divergences from human responses when presented with subtle but truly meaningful variations in prompts or scenarios, as shown so clearly in that moral judgment experiment.
It's a crucial weakness when we expect them to act like us.
It is.
The impressive facade of LLMs can easily lead us to believe they're more human than they are. So, as you continue to interact with AI in your daily life or work, maybe consider this. How much of what that AI generates is truly smart in a human sense, reflecting understanding and reasoning? And how much is just incredibly sophisticated pattern matching that looks smart? And perhaps more pointedly, what novel, subtle changes might uncover the difference? What slight twist in a question or scenario might reveal the boundaries where the simulation ends and the purely statistical nature becomes apparent?
That's a great question to keep in mind.
Thank you for joining us on this deep dive.